We started chapter 9. We looked at the definition of isomorphism and several examples. And we had a few ways of thinking about it. We talked about an isomorphism being a structure preserving map. The existence of an isomorphism, we said, shows us that the two, and we'll see more detail on this, that the two groups are essentially the same. Essentially the same as groups. It will turn out that isomorphic groups, a pair of isomorphic groups, they have any group theoretic type property you care to talk about one of the groups, it'll look exactly the same as the other group. And a very nice way to think about that, to articulate that and to see why that is when you look at the Cayley tables of the two groups. Really what an isomorphism is a way of, and this was the example with U8 and U12, so they've got different Cayley tables because there's different elements in them. This is 1, 3, 5, 7, that is 1, 5, 7, 11, so they look different things in them. However, if you relabel one, they're both 4x4 Cayley tables, and you discover that they have exactly the same pattern and structure under this relabeling, okay? And really, what are these after all? These are really just arbitrary symbols invented by humans, okay? They have some meaning in terms of counting numbers of objects, but when we're looking at groups, we're looking at the existence of the operation on the group and the structure that it has as a group, as a set with an operation on it, and what structure and properties does the operation have. These two are always, whatever pattern you can discover in here will be discoverable in here as well, and will look the same, because these are just relabelings of each other. Okay, so that's a good way to think about isomorphisms as well. It's not a practical way to think about it in terms of if you've got a large group. We don't ever really try and look at the Cayley tables of large groups because they're just unmanageable. But it can be a useful idea to think about. Okay, so we just about got through those examples there. And that brings us to theorem 9.6. So theorem 9.6 starts to put a bit of meat on the bones, or it kind of establishes examples of this claim. So I said if two groups are isomorphic, then we should regard them as equivalent groups. I've declared that whatever group thing you can see in one of the groups, you will also see in the other one if they're isomorphic. Theorem 9.6 starts to show some basic and important examples of that, and we can look through these. So in all of these, so let phi from a group G to H be an isomorphism. So phi is a bijective mapping between the sets G and H, and it has this property, so phi bijection, satisfying what we call the homomorphism property. Phi xy is always equal to phi of x times phi of y for every pair of elements x, y, and g. Now I've omitted the operation symbols. We should understand that G and H are two different groups. Okay, they might consist of different objects. So the nature of the operation in G might be completely separate from the nature of the operation in H. So what's going on in this equation here? Well, in here, we've got x times y, so that's an operation that's taking place in G. And over here, you've got phi of x times phi of y. Well, those are two elements that live in H. So the operation taking place here is the operation in H. Okay? But as is customary, we tend to omit the symbol. But this is one place where you want to keep alive in your mind what operation is going on in which location. So the first property is, well, firstly, it's a symmetric relation. So G being isomorphic to H means that the inverse map, which goes from H to G, is also an isomorphism. So although we defined it as a relation which goes in one direction, G is isomorphic to H, straight away, it automatically means that H is isomorphic to G. Okay, is there much to prove there? Well, clearly, phi inverse is certainly bijective also. Okay? If the map phi is 1 to 1 and onto, firstly, that means the inverse map exists. But secondly, the inverse map will also be 1 to 1 and onto. The only other thing then is how are we sure that it also satisfies the isomorphism property? Well, if we take the isomorphism property for phi, and if x and y are elements of G, there will exist a H1 and a H2 such that 5x is equal to H1 and 5y is equal to H2, or in other words, x is equal to phi inverse of H1 and y is equal to phi inverse of H2. So this isomorphism property, which we have at the top, we can rewrite that as phi of phi inverse of H1 times phi inverse of H2. Okay, so that's just x times y. Just x times y. The operation taking place there is the operation in G. And on the right-hand side, we've got 5x and 5y, but that's just H1 times H2. So we've got a kind of maybe a messy looking statement there, but is there something we can do there to recover the homomorphism property for phi inverse? See, we've almost got it. We've got phi inverse of H1 times phi inverse of H2 here. So what am I going to do to it now? Can you see? On the left-hand side, I've got this phi in the picture, but I don't want to mention phi because I'm trying to build the homomorphism property for phi inverse. So I don't really want this phi to be here. And on the other hand, there's no phi inverse mentioned over here. But I want there to be a phi inverse mentioned on both sides, because in the homomorphism property, you mention the map on both sides, don't you? So there's a nice operation here. I can simply apply phi inverse to both sides. Yeah, you can see that? When you apply phi inverse to the left, it cancels out that application of phi. So you're just left with phi inverse H1, phi inverse H2, and that's equal to phi inverse of simply the right-hand side. So phi inverse of H1 times H2. So that's the homomorphism property for phi inverse. Does it apply for every H1 and H2? Well, I started off, if x and y were in G, then there exists a H1 and H2. But because the map is injective, is bijective, that means for any H1 and H2, there will be an x and y that gets sent to them. Okay, so if there's an x and y that gets sent to them, then we can do this thing and recover the homomorphism. So it does. Since phi and phi inverse are bijective, holds for all. This holds for all H1 and H2. For all H1 and H2 and H. So that establishes that the inverse map is also a isomorphism. So it's a symmetric relation. It's a relationship between a pair of groups. We don't have to specify. If it goes one way, it also goes the other. So we say the groups are isomorphic to one another, but the isomorphism is the map between them. And the second property doesn't really need a proof. It just holds because phi is an isomorphism. Okay, so the two groups have the same sign. So you're happy with that?
Yeah, absolutely.
If the thing. So that's true since phi is an isomorphism. Sorry, phi a bijection. And it even holds for infinite groups, because for infinite sets, the definition of two sets being the same size is the existence of a bijection between them. Okay, so it's a valid statement for infinite sets as well. So in 3, 4, and 5, we really start to see this idea of them having the same group structure come through. So 3 is nice. It says if G is abelian, that implies that H is abelian. Okay? So you can never have an abelian group being isomorphic to a non-abelian. And that makes sense. Being abelian is definitely a group property. Okay? Having it always the case that x times y is the same as y times x. It's something completely expressible in terms of the set and the operation. So it's definitely a group property. Yeah, he's got a nice proof of it here. So we assume G is abelian. We let H1 and H2 be elements of H, and what we want to show is that H1 times H2 is equal to H2 times H1. If we can show that, then that will show that H is abelian. Yeah. And we do it by pulling it back into G. So this product H1 times H2, pulling it back to mapping it back into G, using the abelian nature of G to change the order, and then sending it back into H. Okay. So what do I mean by that? Well, we can write H1 as 5x, and we can write H2 as 5y for some pair of elements x, y, and g. So why is that true? You can't always do that with arbitrary maps, invent pre-images for elements in the codomain, but we can here because phi is a bijection. So there definitely does exist an x which gets mapped to H1 by phi, and a y which gets mapped by phi to H2. In fact, there's unique x and unique y given H1 and H2. So that's true since phi is bijection. Okay, phi is an isomorphism, so if you see 5x times 5y, it's probably the correct thing to do to collapse that into 5x times y. Phi is an isomorphism. Now we've converted the product into a product in G. Because you've got x times y there, and that's a product taking place in G, but we've assumed that G is abelian. So that we can write as y times x. And isomorphism property, so this is 5y times 5x. And 5y is h of 2, 5x is h of 1. So you get the product the other way around. Okay? And that can be done for any pair of elements, h1 and h2 in H. Yeah, because phi is a bijection. So two groups are isomorphic. They have the same abelian status. They're either both abelian or they're both non-abelian. So you can look at that in two ways. You can look at it as, if you know the groups are isomorphic, you then know this fact that they have the same abelian status. Or if you're looking at two groups that have a different abelian status, you know they're not isomorphic. Okay, so this can be used as a tool to detect non-isomorphic pairs. It doesn't tell you that they are isomorphic, right? Just because the two groups are abelian doesn't mean they have to be isomorphic, because they could be of different sizes. Yeah. So alternatively, if G and H have different abelian status, meaning one is abelian and the other isn't, that implies G and H are not isomorphic. And that fits with the idea of structure preserving maps, because if they're different abelian status, it means they've got different structure, different group properties, so they can't be isomorphic. Okay. Cyclic is another one. G is cyclic, then H is cyclic. And of course, all these go backwards. You know, if H is cyclic, G has to be cyclic too. Because remember, isomorphic is a symmetric relationship. So we only have to prove them one way. So here we're showing if G is cyclic, then H is cyclic. So we
We assume G is cyclic. What does that mean? I.e., there exists some element within G such that G is equal to the subgroup generated by G. And that subgroup is the set of all powers G for every integer greater than or equal to 0. Okay, this looks like an infinite set, but of course if G is finite, this infinite set of powers of G will just be repeating the finite list of things in G. So is H cyclic? That's the question. Well, we claim that should have written it down. If we want to prove H is cyclic, we have to show that it has a generator. And what's the obvious generator? 5G. Yeah. So you take the generator that you have G, map it across into H, look at how it behaves over there in H, and we'll see that it's a generator. Okay. Claim 5G generates H. How do we look at this? So we take any element H from H at all, pull it back into G. So there exists an X in G such that 5X equals H. But X is equal to some power of G. Okay, because G is cyclic. So we're using the cyclic nature of G here. X is equal to some power of G, so that implies that 5X, which is equal to H, this is equal to phi of G to the power M. What's the one further operation I need to apply here to reach my conclusion? Trying to prove H is cyclic. We've made a claim now that phi of G is a generator for H. Kind of has to be morally, because we've assumed G is cyclic, therefore a generator for G exists, this special element little g. So we map it across into H, we claim it's a generator. The way we're testing it is we take any element little h from H at all, and pull it back into G. So there exists a little x such that 5x is H. We know G is cyclic, so this x can be written as G to the power m. And then let's look at H again, 5x, which is equal to H. This is equal to phi applied to G of m. There's just one more statement I want to make there. I want to show that little h can be written as a power of 5G. I've claimed that 5G generates H. So I've taken any element at all from H. If I can show that H is a certain power of 5G, then I'll have fulfilled that. Yeah. So which power of 5G is it going to be? There's really only one choice. I haven't yet got a power of 5G. I've got phi of the power of G, not a power of 5G. So can I shoot that m outside the bracket? Can I say that this is the element phi of G, which is my claimed generator for H? Can I say that this is equal to 5G raised to the power m? Yeah. So what am I doing? What am I using there? What's the justification for that? It's not true for any old maps. I can write down definitions of functions where a function applied to a power of x is not the same as taking the function applied to x and raising it to that power. It's only special functions that, well, this is a special function. It's an isomorphism. It's a bijection, but it's not the bijection property we're using here, it's the isomorphism property. Because here we have phi applied to g times g times g times g times g. We want to say that's phi of g times phi of g times phi of g times phi of g. So it's repeated applications of the isomorphism problem. In fact, you may have even proved it as a lemma before that, did he? So repeated applications of the isomorphism problem. With a homomorphism property. Strictly speaking, you'd need induction to prove this in general, but like phi of g squared, well, g squared is just g times g. So the isomorphism property says that's phi of g times phi of g. Okay, normally we quoted that in terms of x and y, but equally well it applies when you're using the same element twice. Yeah, and that is, of course, just phi of g squared. And the same, you get cubes then, because cubed is g squared times g, and so on. So by induction, you get it. So h is generated by phi of g, because we gave ourselves any element of the subgroup H, of the group H, and we were able to write it as a certain power of phi of g. So everything in H is some power of phi of g, so phi of g generates H, so H is simple. Is that okay? Any queries on that?
No, that makes sense.
Yeah. So again, so it's another group property. Two groups are isomorphic. We know they have the same cyclic states. If one is cyclic, so is the other one. If one isn't cyclic, so the other one's not cyclic either. And you can also use it as a tool for detecting non-isomorphic groups. If you see two groups, one of them is cyclic, the other one isn't, you know they can't be isomorphic.
Yeah.
Okay, because it's a group property that is different in the two. And lastly, if G has a subgroup of size n, then so does H. Okay, so having subgroups of certain sizes, that's another group property. You can express that idea purely in terms of the set and the operation. Yeah. So it's an if-then, so we prove it directly. So we let G, what we call it, normally we call our subgroups H, but I can't do that, so we've got H over here, so let's call it K. We'll let K, which is contained in G, be a subgroup of size n. What is the subgroup of H, which also has size n? We have to find it. We have to show that H also has a subgroup of size n. Which, okay, to identify a subgroup, we have to identify a subset. A subset of elements in the subgroup. So which subset is it going to be? And it has to somehow come from this assumption. Now it's not on the page there. Remember what we have. The assumption we're operating is that G is isomorphic to H. So if you've got a certain group structure, group property over in G, we want to show that H has the same thing. So we use the isomorphism. So what's my subset of H going to be? That has n things in it, and that is also a subgroup. Is it going to be K? Well, not K, because K lives over here on the left. It's going to be closely related to K. So the K lives over here on the left. It's a subset of that. That's what I'm writing down, it's a subset going down.
Yeah.
K is a subset of G. What's the subset over here? Well, you use phi. See, phi is your tool for taking stuff here and pushing them over here, translating them over here. So you just apply phi to K.
Yeah.
Phi of K. Maybe that's what you meant when you said K. What is 5K? 5K just means 5 applied to a subset just means the set of every 5 little k, where little k is an element of large k. Yeah, it's just the image of that subset.
Okay, you push that across into the other set. This is the obvious thing. I think it has to be this, sure.
So the claim is this is a subgroup. The claim phi of capital K is a subgroup of H of size n. Is it?
We just have to prove it's a subgroup. So we have to prove it's...
Well, it certainly has size n, since phi is a bijection. See, phi is a bijection on G. It's certainly a bijection on K.
K is just some subset of the elements of G. It's certainly surjective because we're only sending it across to 5K, so it's surjective by definition. So it is a bijection, so 5K does have n things in it. Is it a subgroup? Well, it's certainly non-empty, so it's got n things in it.
Does it have the identity? Now I'll put a subscript H on
the identity because I want to distinguish between the identity element in H and the identity element in G, so they might be completely different
animals. The identity H, is that in 5K? Well, the identity
in H has to be the image of the identity in G. This may be something we haven't actually...
Yeah, something that hasn't explicitly proved, so we should prove this. We can prove this using the isomorphism property, using the homomorphism property. It's true for homomorphisms as well.
A group isomorphism has to send the identity in the domain group to the identity in the codomain group.
So this is certainly an element of 5K.
Because remember, the identity has to be in the subgroup, so the identity of G has to be in K.
Yeah. Is it closed? Is 5K closed? Remember, we're trying to prove it's a subgroup. Well, if you take 2 elements in 5K, I may as well write them as 5K1, 5K2. Everything in 5K looks like phi of something from K. Yeah. So 5K1 is in 5K2. Well, what is 5K1 times 5K2? I want to show that it's in K. In 5K, sorry.
I'm trying to show now that 5K is a closed subset under the operation. So I want to show that the product of those two is in 5K. Now what's the only thing to do here? Combine, yeah.
Use the isomorphism property. Because now the product, you see on the left-hand side there, it's a product taking place in H.
But now the group product here is taking place in G.
And what do we say about K1 times K2?
What observation do we make about K1 times K2? So we took 2 elements in this subset. We pulled them back here, so to speak, because we're now talking about the product of K1 times K2. What observation do we make about K1 times K2?
It belongs in G.
Certainly belongs in G, because K1 and K2 are 2 elements of G. But even stronger than that, belongs in. So little K1 is an element of K, little K2 is an element of K. K is a subgroup. So when you multiply 2 elements from the subgroup together,
in particular, you stay in the subgroup. That's the definition of a subgroup. Yeah. So K1 times K2 is in K. That's what we need. So let's write it as K3 for some K3 in K. What is K3? K3 is K1 times K2. The point is K is a subgroup, so this product has to still live in the set K. But then we're looking at phi of K3, phi of something from K, so that's clearly an element of phi of K, just by definition. Yeah, it's phi of something from K. So this product of elements is in phi of K. So phi of K is closed. Phi of K is closed under group operation in H. So we've shown it's non-empty. It contains the identity. It's closed. The last thing to show it's an element, to show it's a subgroup. Remember the last condition for being a subgroup. So identity, closure, and existence of. An inverse. Inverse, yeah. Every element has to have an inverse. So you let phi of K be an element of K. We're looking for the inverse of this. Again, this is something which we maybe haven't proved, but phi of K inverse will be equal to phi of K inverse. The inverse of phi of K will be equal to phi of K inverse. And this comes from the can be proved using Isomorphism. Homomorphism. And of course, K inverse is in, this is an element of 5K since K inverse is an element of K. That's the okay. K is a subgroup, capital K is a subgroup, so it contains the inverse of every element from itself. And we started off here with 5K, little k, so the little k was coming from capital K. Sorry, this should be 5K there, right? It's 5K there. So it is a subgroup. So 5K is a subgroup of H, and it has the same number of things in it as K, because phi is a bijection. So that's nice. Having a subgroup of a certain size, that's another example of a pure group property that's preserved by isomorphisms. So if you know two groups are isomorphic, whatever subgroup, whatever size you see in one group, you know there must be a mirror or like a image of that living in the other group, and it's a subgroup. Similarly, if you look at two groups and you see that they've got different subgroup structures, this one has like no subgroup of order 5, this one does have a subgroup of order 5, then you know they can't be isomorphic, okay? Or if this one has two distinct subgroups of order 5, two different subgroups of order 5 in it, but this one only has one, then they also can't be isomorphic, okay? Because the isomorphism phi would map those two different subgroups on the left over to two different subgroups on the right. But if we already know that it doesn't have two subgroups of order 5, then there can't be such a phi. Yeah. Okay. So that's term 9.6. Okay, we went quite slowly through it. Okay, maybe didn't get through. Well, we spent some time at the start answering other questions. So we'll push on next week with finishing that chapter and taking in some of the exercises, I think, and then also looking to the next two chapters as well. I mean, the individual chapters aren't very long, chapters 10 and 11 on normal subgroups and factor groups, and then chapter 11 on homomorphisms. But of course, the considerations in in chapter 11 are, quite similar to dealing with isomorphisms, except you're doing it in more general nature because we don't assume the function is a bijection, but it's just some function satisfying the homomorphism property, and we look at consequences from that. But there are natural isomorphisms that you can build out of a homomorphism on related groups, but that involves the factor groups from chapter 10. Okay, so we'll leave it there for now.